Hi again, and welcome to our lecture on sum and difference formulas in trigonometry. Today we'll see some formulas involving the sine of a sum, the cosine of a sum, and the tangent of a sum, as well as sine, cosine, and tangent of differences. These formulas, needless to say, are very, very important in calculus courses. And not only these formulas, but they'll give rise to some other very useful formulas when you go on and take calculus. Here's the sad news. The sine of a sum of two angles is not the sum of the sines. Remember back when we did logarithms? We had the same bad news there. The logarithm of a sum was not the sum of the logarithms. It was the log of a product was the sum of the corresponding logarithms. Well, here the formulas are a little bit more complicated. So, again, it's sad news, but the sine of a sum is not the sum of the sines. Here are the correct formulas. The sine of u plus v, where u and v are arbitrary real numbers, equals the following. Sine of u times cosine v plus cosine u sine v. Fairly complicated. Trust me, though, I found over the years students have this formula memorized pretty quickly. Sine of a difference is sine of u minus v, and it's almost the same formula, but you change the plus to a minus. Sine u cosine v minus cosine u sine v. And then there are similar formulas for cosine. Cosine of a sum is cosine u cosine v minus sine u sine v. Unfortunate, I'm sorry. The cosine of a sum involves a minus sign, and conversely, the cosine of a difference, cosine of u minus v, involves a plus sign. It's cosine u cosine v plus sine u sine v. So those are the formulas. Students often ask me, where do these come from? Why are these true? And many pre-calculus books would have a proof of these formulas. The proofs are fairly complicated, and I don't think add much to their understanding. Let's apply these formulas. Let's see how they work. Let's try to calculate the sine of a certain angle that up to now we couldn't calculate. Pi over 12, say. Can we calculate the sine of pi over 12? That's not one of our favorite angles, is it? We aren't real comfortable with pi over 12. But watch this trick. Write pi over 12 as a difference of two angles. It's pi over 3 minus pi over 4. You can check that by getting a common denominator and cross-multiplying. So sine of pi over 12 is the same as sine of pi over 3 minus pi over 4, and that's the sine of a difference of two angles. We can use our new formula. Here it goes. It's sine of the first, cosine of the second, minus cosine of the first, sine of the second. In other words, it's sine pi over 3, cosine pi over 4, minus cosine pi over 3, sine pi over 4. And these angles, pi over 3 and pi over 4, are friendly angles, angles that we know about. Sine of pi over 3, what's that? Square root of 3 over 2. Cosine pi over 4, right, square root of 2 over 2. How about cosine pi over 3? That's 1/2, and sine of pi over 4 is square root of 2 over 2. Bundle those together, and you get square root of 6 minus square root of 2 in the numerator, and you get 4 as your common denominator. So there's the final answer. An unusual looking answer, isn't it? Kind of amazing how that worked. That answer is square root of 6 minus square root of 2 divided by 4. On a calculator, you can get, of course, the decimal approximation of that answer, which is about 0.256619. And my fancy calculator, which gives more exact answers, doesn't quite give the answer in that form. It said the answer was the quantity square root of 3 minus 1 times square root of 2, all divided by 4. But we know about this game. Those are the same answers, aren't they? They're just written slightly differently. Okay. Now, if you look in a pre-calculus book or a calculus book, you'll see these formulas written slightly differently. They'll combine them. Let me explain what I'm talking about. We have a formula for sine of a sum, and we have a formula for sine of a difference. And the formulas are basically the same, except on the other side, there's a plus sign for the first one and a minus sign for the second one. So here's how they write them. Sine of u, and they use a symbol called plus or minus v. We saw that symbol actually in the quadratic formula, didn't we, a few lectures ago? And then that's equal to sine u cosine v plus or minus cosine u sine v. And you read this as follows. If you're doing the plus sign on the left, so the upper plus sign, you would use the plus sign on the right, and conversely, the minus signs. So it's two formulas bundled into one. Now, the cosine formula gets bundled in a curious way, because remember, the cosine, the minuses and plus were interchanged. So here's how you would write it. Cosine of u plus or minus v equals cosine u cosine v minus plus. Isn't that bizarre? Minus plus sine u sine v. And so if you use plus on the left, you would use the minus on the right. And that's how you'll see them in textbooks. You'll see them written this way. It saves a little bit of ink. They can compactify the formulas. Okay. Let me use the cosine formula to verify something we saw earlier dealing with the cofunctions of complementary angles. Remember, we talked about the cosine of x minus pi over 2 is the same as sine x. And we kind of illustrated that with a right triangle. Let me illustrate this formula, or prove it, using our new cosine formula. Here we go. I'm going to start with the left-hand side, cosine of x minus pi over 2, and do some mathematics and end up with sine x. I'm proving this identity. Here we go. Cosine of x minus pi over 2 equals. Well, that's cosine of a difference, x and pi over 2. So the formula says it's cosine x, cosine pi over 2, and now it's plus, isn't it? Remember, if it's minus over here, it's plus sine x, sine pi over 2. Now we can evaluate some of these. Cosine pi over 2 is 0, and sine pi over 2 is 1. So it simplifies to cosine x times 0 plus sine x times 1, and that, of course, is just sine x. Let me show you a picture of this. I claim this is really a shift. And savor these two graphs for a moment, one on top of the other. On the top, I have our friend, the sine curve, and on the bottom, I have cosine. Well, the formula cosine x minus pi over 2, you remember when we analyzed these trigonometric graphs, that's a shift to the right of pi over 2 units. So imagine the following. Look at the cosine graph and move it to the right pi over 2 units. It'll be exactly equal to the sine graph, won't it? Just shift it over and you've got the sine graph. So that's what we're talking about here. We're shifting one curve to get the other. All right, on to the tangent formulas. We've had the sine and cosine. They weren't too bad. Well, there's a formula for tangent of a sum and a difference. Let me show them to you. They aren't very pleasant, and fortunately, they don't come up in calculus courses too much. And if they do, what I always do as a teacher is I tell the students on the exam, hint, here's the formula for tangent of a sum, because I don't expect people to memorize these. But you probably want to see them. Here they are. Tangent of u plus v, tangent of a sum, equals, it's a quotient. In the numerator is tangent u plus tangent v, and in the denominator it's 1 minus, ouch, minus tangent u times tangent v. Don't blame me that it's complicated. This is the nature of mathematics. Trigonometry is not as nice as we'd like it to be sometimes. And a similar formula for tangent of u minus v, the only difference is the minus and plus sign get interchanged. So it's tangent u minus tangent v in the numerator, and 1 plus the product tangent u tangent v in the denominator. And again, you can mold these two into a single formula using those symbols plus minus. So tangent u plus minus v, the numerator will have the same symbol plus minus, and in the denominator will have that funny looking symbol minus plus, because the signs differ, don't they? So that's the formula for tangent of a sum or a difference. Let's use that formula to sort of see how it rolls. I think you'll find it pretty easy to plug in the numbers. Let's show that tangent of theta plus 3 pi is indeed tangent of theta. Let's just show that using the formula. So it's tangent of a sum. Here we go. Tangent of theta plus 3 pi equals tangent of the first plus tangent of the second. That's the numerator. So it's tangent theta plus tangent 3 pi. What about the denominator? Well, now it's 1 minus the product, tangent theta times tangent 3 pi. Well, things simplify, don't they? What's tangent 3 pi? Well, tangent 0, tangent pi, tangent 2 pi, tangent 3 pi, they're all equal to 0. And what about in the denominator? We also have a tangent 3 pi. That's also 0, which simplifies the denominator enormously. And we're left just with tangent theta. The numerator's tangent theta, and the denominator is just 1. Now, of course, this example was kind of trivial in a sense, because you already knew the answer, didn't you? You remember that the tangent function is periodic with period pi. It repeats itself period pi. Remember that graph? It has those chunks that all look alike, and the period was pi. So tangent theta plus 3 pi is obviously tangent theta. Okay, great. I'd like to pause now and do an example from calculus. This is a big jump from what we've been doing. This is, we're actually going to do a somewhat deep calculus topic. And it's not going to be important for what follows, but I thought I'd give you a taste of calculus, try to encourage you to study calculus after you take this pre-calculus course. And I'm going to look at an expression that occurs in calculus courses, and I'll tell you where it comes from. In fact, here's what's going to happen in this problem. We're going to compute the slope of the cosine curve. We're going to compute the slope of the tangent line to the cosine curve. So this is, again, is a big quantum jump from what we've been doing in this pre-calculus course. But I think you might find it interesting to see how pre-calculus plays such a big role in calculus. So I'm going to begin by analyzing a certain kind of obscure expression. The numerator is cosine x plus h minus cosine x, and the denominator is just h. H is some small number. Think of h as being like 0.01, some little bitty number. Now, where does that come from? Let me motivate that expression. Here's a picture of the cosine function, our old friend cosine x. I've labeled one point on the curve x cosine x. And then I've labeled a nearby point, x plus h. H is a small number, so that point is near x. And then the y-coordinate of that point would be cosine of the quantity x plus h. So I have 2 points on my cosine curve. X comma cosine x is 1 point, and the next point is nearby. Its coordinates are x plus h cosine x plus h. All right, ask yourself the following. What's the slope of the line joining those 2 points? That slope is very close to the slope of the tangent line to that curve at x. Well, the slope, you remember from algebra, is the difference in the y values divided by the difference in the x values. So it'll be cosine x plus h minus cosine x, that's the difference in the y values, divided by x plus h minus x. The x's cancel and you're left with h in the denominator. That's the expression I started with. The slope. The numerator was the difference in the y values. The denominator was the difference in the x values. So it's not such an obscure expression after all. It's an expression giving slope. And now I'm going to simplify it. I'm going to use our new formula, cosine of a sum. And that's cosine x cosine h minus sine x sine h. And then at the right I have minus cosine x, all divided by h. Here we go. We're going to analyze this a little closer, and this is taken from an actual calculus book. We factor out cosine x. Cosine x occurs in the first term and the third term in the numerator. So it's cosine x times the quantity cosine h minus 1, and then the other term is minus sine x times sine h. And now do some more factoring. It's cosine x times the expression cosine h minus 1 over h, and then minus sine x times the expression sine h over h. Okay, so we've simplified this expression for slope to a difference of two kind of ugly terms. But now you might recognize the second one there, sine h over h. We saw it last lecture as sine x over x, but the variable doesn't matter, sine h over h. And I ask you the following question. It's not defined when h is 0, is it? That's obvious. But when h is really small, what is that approach? Do you remember what sine x over x was when x was really, really small? Yes, it was close to 1. Remember, we used that limit notation? The limit was 1. Even though it's not defined when h is 0, when h is close to 0, that quotient gets closer and closer to 1. Okay, good. Now, what about that other term in parentheses, the cosine h minus 1 divided by h? Well, in a similar fashion, you could graph it, and you would discover that it gets closer and closer to 0 as h gets close to 0. So let's go back to our picture. Imagine h very, very small. In other words, x and x plus h are almost next to each other. That means that line joining the 2 points is pretty much looking like the tangent line to the curve. Okay? And what is the slope of that tangent line? Well, that expression gives the slope. We notice that the first term, the cosine h minus 1 over h, approaches 0, and the second term, sine h over h, approaches 1. So as we get closer and closer, this simplifies to minus sine x. Everybody else has died off. The cosine x times 0, goodbye, and the sine h over h is 1, and sine x times 1 is sine x. So, what's our conclusion here? You just did a key calculus derivation. I'm going to use a fancy word for you. You just found the derivative of the cosine function. The derivative of cosine is minus sine. Wow, you just did calculus. All right, I won't do too much more calculus because this course is pre-calculus, but trust me, if you go on and take calculus, you'll see this again. And maybe you'll sort of ring a bell. You'll go, oh yeah, I remember in my pre-calculus lectures, I saw something like this. It's kind of amazing that these pre-calculus skills can now be used to do something where we calculate the slope of a curve. Wow, all right, enough heavy calculus. Let's go back to some more comments about what we've been doing with our pre-calculus and our functions, our trigonometric functions. One thing you might have noticed in that last derivation, there was a notational thing that I did. I did sine of h and cosine of h. And there was a reason why I didn't write it as sine h with the h right next to the word sine. In other words, S-I-N-H as 4 letters in a row. The reason is, it's kind of curious, there's another function in mathematics called hyperbolic sine. and we like to say it's called sinh, S-I-N-H. It's on your calculator also. Now, it's usually hidden in some menu, but the hyperbolic sine is another function that's out there. It's not part of pre-calculus, don't panic, but I wanted to make sure we didn't mix it up with the sine of h and sinh. And there's also one called cosh, hyperbolic cosine. So if you're very curious, look at your calculator manual and you'll see where these functions live. All right, I mentioned there were other important formulas related to these sum and difference formulas. Let me dabble with a couple of them, show you some other formulas that play a big role in trigonometry and calculus. One set of formulas are called the double angle formulas. Sine 2 times an angle, like 2u, the sine of 2u. How could we figure out that in terms of simpler sine functions and cosine functions? Well, use the sine of u plus u. 2u equals u plus u, and now use our formula. That's equal to sine u cosine u plus cosine u sine u, the same thing twice. It's 2 sine u cosine u. So that's a nice formula to memorize. Sine 2u equals 2 sine u cosine u. There's a similar formula for the cosine 2u, and here's how it goes. That's cosine of u plus u, which equals cosine of the first, cosine of the second, minus sine of the first, sine of the second. So it's cosine u minus sine u, or cosine squared minus sine squared. And you'll see it written that way many times. And you'll see it written a couple of other ways as well. You can take that sine squared and use the fundamental identity to write it as 1 minus cosine squared, and then you get 2 cosine squared minus 1. Or you can do even something different. Take the cosine squared and write it as 1 minus sine squared. And then you get the equivalent formula, 1 minus 2 sine squared u. So cosine 2u has 3 formulas. They're all true, and it's good to be aware of all 3, although if you memorize the first one, you can derive the other 2. The important one is cosine 2u equals cosine squared minus sine squared. Let's apply some of these formulas to an example. Let's solve the equation 2 cosine x plus sine 2x equals 0, and let's solve it on the interval 0 to pi. So I want to find all x values such that 2 cosine x plus sine 2x equals 0. And already we're sort of going, well, wait a minute, I'm not sure how to untangle that sine 2x. But we have a formula for that, don't we? So we can write it as 2 cosine x plus 2 times sine x cosine x. The sine of 2x has a formula. It's equal to 2 sine x times cosine x. And that's all equal to 0. Factor out 2 cosine x, and you're left with 1 plus sine x equal to 0. A product equals 0. One of the terms must be 0. If cosine x is 0, what's x? And we're back to one of these basic skills. Can you think of an x value such that the cosine is 0? And we're on the interval 0 to pi. Yeah, pi over 2 and 3 pi over 2. The other term was 1 plus sine x. That means sine x is minus 1. So what's x? Well, if sine is minus 1, x is also 3 pi over 2. We get kind of a repeated answer here, don't we? So the final answer on the interval 0 to pi are pi over 2 and 3 pi over 2. If you wanted to write these on the entire real line, you would add multiples of 2 pi, wouldn't you? You'd get pi over 2 plus 2n pi and 3 pi over 2 plus 2n pi. And then you might be very observant and know that you can compactify those two and write the final answer on the entire real line as pi over 2 plus n pi. N here is an integer. Here's a graph of the function 2 cosine x plus sine 2x on the interval 0, 2 pi, and then you see the roots, pi over 2 and 3 pi over 2, and they're repeated because of the periodicity up and down the real line. Let's do an application to televisions. I finally bought a flat screen television, and I noticed something, that the diameter was, or the diagonal was 54 inches, and the angle that the horizontal made with the diagonal was 37 degrees. So I asked myself, what's the area of my TV screen under this scenario? So how big is the viewing area of a TV? They're kind of rectangular in shape, given the following dimensions. You have a diagonal of 54, and you have an angle of 37 degrees. So here's kind of a picture of a television set. I've labeled the diagonal D, and there's also a height H and a base B, and then the angle theta is the angle from the horizontal up to the diagonal. And let's find the viewing area under this scenario. Okay, so the area of our television is area equals base times height, B times H, and we can figure out B and H using trigonometry. Look at the figure. Sine of theta is opposite over hypotenuse, so that's the height over D, H over D, and cosine is B over D. So sine theta H over D yields H equals D sine theta. Cosine is B over D, so B is D cosine theta. So we now know the height and the base in terms of D and theta. The area is base times height, so it's D cosine theta times D sine theta. Mold them together, D squared sine cosine. And now I can do a little trick, multiply that by 2 and divide by 2, and magically you see the expression 2 sine theta cosine theta, which is nothing more than sine 2 theta by one of our new formulas. So I've expressed the area, the viewing area, as D squared over 2 times sine 2 theta. You give me a value of D and give me a value of theta, I'll tell you the viewing area. For instance, if D is 54 and theta is 37 degrees, you plug those in, 54 squared over 2 times sine of 2 times 37 degrees, use your calculator, and you get 1,401.5 square inches approximately. Now, is that an optimal area? I know that televisions aren't supposed to be square. There are technical reasons why they are rectangles. But if you had a square television, you would have a different area, wouldn't you? And it would be the largest area possible. Let me show you why. The expression for area is D squared over 2 sine 2 theta. Well, what would make that expression as big as possible? Well, the sine goes between -1 and 1. It'll be biggest when it's 1. And hence, you would let the angle be 45 degrees, and then sine of 2 times 40 is sine of 90, which is 1, and you get the maximum viewing area, 54 squared over 2. That's slightly bigger. It's 1,458 square inches. Okay, let me also mention very briefly, there are a couple of other formulas that occur in calculus that I thought I'd put on the table for you. We won't use them in this course, but they are called power-reducing formulas. One of them is sine squared u equals the quotient 1 minus cosine 2u divided by 2, and then cosine squared u is 1 plus cosine 2u divided by 2. And there are many, many, many more formulas. It goes on forever. If you look at the back of a textbook or the back of our workbook, you'll see a list of the most important formulas, but one can be overwhelmed by this. There are just so many formulas, some very obscure ones. But today we've sort of given the basic formulas that I hope you'll sort of be comfortable with as we move along in our study of trigonometry. So what are we going to do next time? We're going to really change gears next time. We're going to go back to sort of the beginning of trigonometry and look back at that right triangle which gave birth to the trigonometric functions. And we're going to use something called the law of sines. We're going to study triangles, and given certain information about the sides or the angles, we'll be able to figure out the other sides and the remaining angles. So we're kind of going back to studying triangles again. I think you'll really enjoy it, and it has some very interesting applications. So I'll see you next time. Thank you.